All right. So let's pick up where we left off last time. We had talked about this extra bit of stability that comes with being an aromatic compound, and that although aromatic compounds contain a bunch of double bonds like alkenes, we don't classify them in the same group, right? Because they don't behave the same chemically as alkenes. They do not undergo those addition type reactions, okay? Again, that's not to say that they don't undergo reactions, and today we're going to learn about that type of reaction. Okay, so reactions of our aromatic compounds. These are what are called electrophilic aromatic substitution reactions. And I ran out of room. All right, electrophilic aromatic substitution reactions. That's like the type of reaction that these aromatic compounds undergo. This word electrophilic, do you guys know what that ending means, philic? If something is a phile for something, it's I don't really know the origin, Greek or Latin or something like that it means a lover of that thing, okay? So these are electron lovers, meaning they love those benzene rings. All right, those benzene rings have a lot of electron density because of those double bonds, right? Those delocalized electrons that move around these rings. So we're going to see that our aromatic compounds like benzene, they react with what we call electrophiles, these electron lovers, things that really like electrons. I think the more important word in here is the substitution word, okay? This is in contrast to addition reactions. In addition reactions, we were adding something to either side of our double bond. For substitution reactions, we're going to be substituting or swapping atoms, okay? So swapping. All right, so what do I mean by that? So kind of like this generic formula that we're going to see over and over again is our aromatic compound like benzene. We're going to combine it with some electrophile. We're going to leave that as just this E. Okay, put a positive charge on it because it loves electrons. And what we're going to see is that one of those hydrogens on the benzene ring gets replaced with that electrophile, right? It gets substituted for that electrophile. Right, so again, this is in contrast to addition reactions. I'm not adding something to either side of that double bond. I'm substituting one of those hydrogens for whatever this electrophile is. And we're going to see a few different electrophiles in this chapter, okay? But importantly, again, this idea that I'm just swapping out this hydrogen for whatever that electrophile is. That's the same basic formula we're going to see for all of these reactions.
I see that you have a hydrogen on where the E used to be. Is that going to keep none of that?
I mean, for our balanced chemical equation, if we needed to do some math, right, we'd need this balanced chemical equation. Typically in organic chemistry, the only thing that we care about is the organic product, right? That's the one that I'm going to make sure that you know how to draw. Okay. Did we break our aromaticity in our product here? Right? So that's the big important part about these reactions is they maintain that nice stable aromatic ring. Right? It's not that we don't have any reaction, but we definitely aren't going to break our nice stable aromatic ring. We're just going to swap out a hydrogen for this, what we call electrophile. All right, so we're going to have a few different ones. All right, again, we're going to start with our benzene here. Okay. The first one is going to react with bromine. We saw this with regard to alkenes and addition reactions, but again, it's not going to be an addition, okay? And what we're also going to see with all of these reactions is that they require some sort of a catalyst. Benzene is not terribly reactive all by itself. There has to be some catalyst in there that's going to help promote this reaction. All right, and in the case of bromine, this reaction will occur in the presence of iron bromide, iron 3 bromide. All right, what do we know about catalysts? Does anybody know, have we ever heard of a catalyst before? All right, so what do we know about catalysts? Okay, what's up? It helps the reaction occur, and in particular, it helps speed up the reaction, okay? It doesn't actually like change the thermodynamics of the reaction. If you let this reaction sit for 1,000,000 years, you would get the same amount of product as if you use the catalyst. We just don't have 1,000,000 years, right? So we put a catalyst in there to help speed up a reaction, okay? So let's just make note, catalysts, that's this guy here. They do two important things. They increase the reaction rate. All right, but there's one other very important feature of a catalyst, which is that it's never consumed in the reaction. It's kind of just sitting there on the sidelines, making sure that everything goes okay, but it's not actually participating in the reaction. It's not consumed. I'll have the same amount of iron 3 bromide after I get done with this reaction as I started with, okay? Importantly, that means I'm not going to see any iron in my product, right? Because the iron isn't consumed in this reaction. It's not what's being incorporated into this molecule. So when we're trying to predict products, there's always going to be this catalyst there. But really, we're looking at this thing over here to give us a clue as to what our product's going to be. Okay? In this case, what I'm going to swap out is a hydrogen and replacing it with a bromine. All right, and just to be good, again, this is the one that I'm going to be concerned that you know how to give me, but just because everybody's like, well, wait a minute, we started out with Br2, what the heck happened to the other bromine? That gets incorporated with that hydrogen that we lost, okay? And again, I'm not really too concerned about my inorganic product, but just to make it clear that there's two bromines on the left, it's not like one of them magically disappears or anything like that. It's just that it gets incorporated into our inorganic product, hydrobromic acid. HBr. Okay, so it's only one of these bromines that we're sticking on there. All right. Importantly, this really wouldn't make any sense to put a 2 there anyway. Okay, bromine would have too many bonds. You'd have to have some formal charge business. You just can't just stick a Br2 on anywhere. All right, so it's only one bromine that's going to be incorporated onto that ring. And again, importantly, I've gotten a substitution reaction, so I'm substituting this hydrogen for that bromine. All right, so then by analogy, what do we think is going to happen when I put in chlorine in the presence of iron 3 chloride? Same thing, except for, right, different element. All right, so everybody take a second and predict my product here. right, so same idea. I've swapped out one of these hydrogens for now just a chlorine. And if I'm good, I can put my HCl over there. But again, substitution reaction, this hydrogen being replaced by this chlorine here. All right, I'm not breaking my aromaticity. I'm not breaking any of those double bonds. I'm just swapping out one of the hydrogens on my benzene ring for one of those other elements. All right. The next one. Actually, I'm going to put this on a different page. So again, starting out with benzene. This reacts with nitric acid, HNO3. In the presence of sulfuric acid, that's my catalyst here. Okay. This is going to replace one of these hydrogens with NO2. All right, and again, I can draw my inorganic product, which is water. This is, NO2 is something new that we haven't seen before. This is what's called a nitro group. All right, and although you'll see it written like that NO2 abbreviation, I'm going to draw out the full Lewis structure of this so we can take a look at it. We're used to seeing nitrogen with how many bonds? What does it usually like to have? 3 bonds and how many lone pairs? 1, right? Okay, that's not the case here. So let's draw out this Lewis structure explicitly so we can see what this nitrogen looks like. All right. How we create a nitro group. We have our nitrogen. It's double bonded to one oxygen, but then single bonded to the other oxygen. All right, let's zoom in here. We said that nitrogen likes to have 3 bonds in one lone pair. Here it has 4 bonds, right? So what's the formal charge on that nitrogen if it has 4 bonds? It's going to be positive, right? It's got more bonds. Oxygen likes to have how many bonds? 2, and so if it has 2 bonds, it has how many lone pairs? 2. So this oxygen up here is normal and happy. But what about this oxygen with only 1 bond? How many lone pairs must it have? 3. And then its formal charge would be, now that it's got more lone pairs, it's going to be negative. Okay? So this group is pretty weird. You can see that all together it's neutral, right? I got 1 positive charge and 1 negative charge. But importantly, this nitrogen does not have any lone pairs on it, which is going to be important later on. Okay? So again, when you're doing your homework, when you're doing your exam, it's cool to write it NO2. That's fine. But we do want to make a note that in our nitro group, there are no lone pairs on that nitrogen. Again, that's going to be important later on. All right, so our next reaction is with sulfuric acid. And this one's a little weird because you do have to catalyze the reaction, but what you do is it's called fuming sulfuric acid. Basically, you just mix these two together and you boil the absolute crap out of it. And the reaction actually takes place in the gas phase with the sulfuric acid fumes. Okay, so we call it fuming sulfuric acid. We'll again have a substitution reaction. This will now be an SO3H. Okay. This is what we call a sulfonyl group. All right, and then again, let's kind of draw out the full Lewis structure. You're going to see it abbreviated like that, but just because we need to make a note about its lone pairs here. We got a sulfur in the middle. It's got 3 oxygens. 2 of them are double bonded. And then it's got an OH on there. All right.
We'll never see like the reaction, like ever take a double bond from the cycle.
No, it will never break because otherwise it's no longer aromatic, right? So the whole idea is that these aromatic compounds are super stable. So it's going to be aromatic over here and aromatic over there. That's the whole big difference between these reactions, is that they preserve that aromaticity, right? By swapping out that hydrogen, I didn't change this compound from being aromatic, and that's the really important feature of these reactions. And if we're good, we can kind of note there's also water over here that's being produced. All right, this is really weird. We don't see this a lot in organic chemistry. It's not a big deal because we're usually focused on just carbons and oxygens and nitrogens, and they like never have more than 8 electrons in their octet. The bigger elements sometimes can have more electrons in their octet, which is why sulfur has so many frickin' bonds here. Okay? We don't really need to pay attention to all that. What we really need to make note of is, just like we said with the nitrogen, there are no lone pairs on this sulfur. And again, the lone pair business is going to be important here in a bit. All right, so we're going to have 6 of these reactions in total. We've learned 4 so far. So first of all, a bunch of new reactions. What are we going to do when we get home? Flashcard them, right? Add them to the pile of these reactions that we need to know, because we need to be able to see these combination of reagents and know that that leads to a certain product, right? So we just want to have that kind of drilled into our brain. We'll learn 2 more, but before we do that, let's just kind of practice. Let's make sure. So everybody flip to a new page. We're going to see what we can do for memory here based on what we just learned. I guess let me do it in the same format. All right, so again, we have our catalyst here, but that's not really what's going to tell us what our product is because it's not actually involved in the reaction, right? So I'm looking over here for my clue. Unfortunately, it's not as easy as just saying, all right, boom, just like that, right? In this case, it's just one of those chlorines from that Cl2. Okay? Likewise, with this HNO3, okay, I lose one of those hydrogens and one of those oxygens, right? So what gets put on there is just NO2. So not the exact same as what's over here, but that's what I'm going to look at for my clue. Okay, so this is really important because these are one of these problems that if you do them with your notes open, it's going to be really, really straightforward, right? To play the matching game. But we need to know that there's not 3 oxygens on here, there's only 2, and we're not going to have our notes on the exam, right? So make sure that you're practicing this with your notes closed as well so you can actually make sure that you know, okay, given this, that's not HNO3 over here, but just NO2. Right? Slightly different. Obviously, there's a big, big clue as to what you put looking over here, but it is slightly different. Okay, so again, just make sure to practice this stuff with your notes closed as well. All right, and of course, as you saw in your last exam, there's this reagent bank that you're going to be given, right? You just need to be able to spy it, but from memory, what would I put here that I would use along with my iron 3 bromide to stick a bromine on there? Br2. Cool. Okay, so the next 2 reactions have a special name. The 2 scientists that came up with them, Friedel Craft. Did I spell that right? Well, doesn't matter. All right, and what we're going to see that's a little bit different with these Friedel Craft reactions than what we've seen before is they're going to create new carbon-carbon bonds. All right, up until this point, we have not seen any reactions that actually make any new carbon-carbon bonds. All right, so the first one, again, we got our benzene ring. First one is going to use an alkyl chloride. What does that word alkyl sound like? What functional group have we learned about?
It has,
Alkyl is kind of like alkane. So this is just an alkane that has a chlorine sticking off of it. All right, so I'm going to use a specific example here. Our catalyst is actually our familiar iron 3 chloride. I'm again going to be doing a substitution reaction. Okay? But importantly, what I'm going to be doing is I'm going to be creating a new carbon-carbon bond in these reactions. Specifically the carbon at the base of that hydrogen, right, that I'm substituting out, which is the same carbon that I've been creating a new bond with all along. But I'm going to be creating a new bond between this carbon and the carbon at the base of that chlorine. Okay, so in my reaction here, again, I've connected, let me actually color code them something a little bit different. I'm connecting my orange carbon from my benzene ring with that blue carbon that was at the base of that halogen. All right, so we're going to create a new carbon-carbon bond, and specifically we're going to connect carbon on benzene with carbon at the base of that chlorine. Okay, this same reaction you will see in this sort of more generic format, which I don't think we've seen before, where you say benzene plus RCl. This R is kind of like a variable. I don't know why they use R in organic chemistry. But this R is like a variable that stands for any amount of carbons and hydrogens, right? So it's just telling you there's some big ol' alkyl group on that chlorine. I don't know what it is. I don't know if it's 1 carbon. I don't know if it's 50 carbons. Whatever it is, it has a chlorine attached to it. All right, again, it's kind of like a variable. All right, and what happens is we stick that R group onto that ring. What's up?
So you don't have to label the chlorine on these ones?
You don't have to label the chlorine. What do you mean?
You don't have to put the CO like on
The CL is going to be gone. It's going to be kicked off over here. It actually, oh, sorry, first of all, I meant my catalyst. It's over here somewhere. It kind of gets shoved off altogether and gets replaced by the actual benzene ring on that R group. Okay, so on the one hand, there's really nothing different than what we've seen up until now. Okay, what's going to make these a little bit tricky though is because this can be anything, right? We got to be able to see how we connect these things for any like size number of carbons, right? If it's 1 carbon, it's going to be pretty straightforward. For this one, it was 3, so we had to make sure to connect it at the right place, right? Again, the one thing that's going to make these a little bit different is that this R group can be any number of carbons. So let's just practice this real quick and make sure that we have our connectivity down. We'll do 2 different Friedel Craft. Oh, I guess it is HCl. Well. right, so I'm going to attach the carbon on my benzene ring. And just to be clear, I've kind of arbitrarily picked this one in this top, what is that, top right corner, just because it makes the drawing easier. It keeps everything kind of in one line. You could pick any of them, right? This ring is perfectly symmetrical. You could rotate it around and put it anywhere, right? It'd be the exact same thing. But importantly, I'm going to connect that carbon to the carbon at the base of that chlorine. So when I draw this bond, that's that carbon there, okay? Because we're growing our carbon chain, counting carbons is going to be a really important double check, right? I should have the same number of carbons on the left-hand side as I have on the right-hand side, okay? And just to be clear again, we sort of really what the homework assignment's going to be asking you for, what I'm going to be looking for on the exam is the organic products. The other one, it's actually HCl, not just chloride. This inorganic product, in each of these, there's always some inorganic product that would help balance your chemical equation. Might be HBr or HCl or water. What we care about is what's happening to the carbons. That's the most important thing in organic chemistry. All right, and so this next one, you can see how it's going to be kind of a pain in the butt. The bigger the carbon, the larger the number of carbons you're adding, the sort of more difficult it is. I'm going to connect this with the carbon at the base of that chlorine. All right, so here's my benzene ring. Here's this. I'm going to draw my new bond. That means that that's this green carbon here, okay? But I gotta include everything else that that green carbon's attached to, right? So I have one group coming up, so I have this little fork coming off over here, and I have another one sticking off over there. Right? I had, importantly, and again, counting carbon is going to be really important, I had to include all 1, 2, 3, 4, 5 carbons from my original molecule over here. 1, 2, 3, 4, 5.
So whatever point you pick, that's the point you gotta start with. So you might pick the green point from the Cl group.
And it has to be that one, right? You can't just pick any one. It's got to be the carbon at the base of that chlorine that you're attaching. So you're kind of like picking this thing up and sticking it on over here, right? But again, so I guess I pick it up without the chlorine and sticking it on over there, right? That's what we're doing. But again, yes, it has to be the carbon at the base of that chlorine that's getting attached. Okay? And that's what's going to make these problems a little bit, when it's bromine, it's just bromine every time, right? It's just you put Br, not a big deal. For these ones, there can be any number of carbons and hydrogens, which is what's going to make it a little bit trickier. We get big, ugly products from these reactions because we're actually growing our carbon backbone here, growing the number of carbons we have. So we have a question over here. What's up?
You don't have to label the chloride on the right-hand side of the slide.
So again, you can put HCl if you're trying to be good, but what anybody ever cares about is your organic product, right? And that's what your homework assignment will be looking for, is your organic product. Okay. So the other one is very similar. Same dudes discovered it, Friedel Craft. Got a benzene ring, but this is going to use, so we got another chlorine, but this is going to be attached to this carbon oxygen, or this carbon that has an oxygen double bonded to it. Okay, so actually before we even, well, I guess we can look at our product real quick. We can see that it's actually the same game. So the carbon at the base of that chlorine is what's going to be stuck onto my ring, just like we saw with our other Friedel Kraft reaction. All right, so everybody take a second by analogy, see if you can't predict our products here. Importantly, that oxygen's not going to go anywhere, right? You're still going to have that oxygen-carbon double bond in your product as well. You're just picking this thing up and attaching it to the carbon at the base of that chlorine. All right, so again, visually kind of what I'm doing is I'm picking this up and I'm replacing that chlorine with that benzene ring, right? Creating a new bond between the benzene ring and my carbon at the base of that chlorine. So I got that. And then I got to, again, count carbons. So I got 1, 2, 3 carbons to stick on there. All right, again, tap, tap, tappa. Make sure you got the same number of carbons on both sides. This is what's called an acyl chloride. We can, similarly to before, we can do this in a more like kind of, this was a specific example. We can do kind of like a generic formula here. Because just like before, this acyl chloride can be any number of carbons. Importantly though, it does have to contain that carbon-oxygen double bond. So that's all, that part's always going to be the same, but the back end can be however big or small. All right, so again, that R group saying any amount of carbons.
So what is it, the acyl or?
Acyl.
Acyl,
Yep.
acyl contains a carbon and oxygen bond?
Yes. And specifically, the chlorine is attached to that carbon with the double bonded oxygen. All right, so we'll draw some products here in a second. There is something I want to, terminology here that's going to be important. This carbon-oxygen double bond plays a huge role in organic chemistry. We see it all over the place in a ton of different functional groups. Biomolecules are littered with these things. They have their own special name. Okay? This is what's called a carbonyl bond. All right, and so you're going to hear this terminology all the time referring to this type of bond, and specifically this would be called a carbonyl carbon. Right, the carbon that's in that carbonyl bond, and this a carbonyl oxygen. Okay, so if we go back to our reaction here, we see that it's that carbonyl carbon that's being attached to my ring. Right? We're going to see that with all of these Friedel Craft reactions, with all the acyl, starting with the acyl chloride. All right, okay, so then again, let's just practice. Let's say we got a benzene ring. Get this part out of here. All right, so again, I'm going to attach my benzene ring to the carbon at the base of that halogen, which we just learned is called a carbonyl carbon. And I need to make sure to include all those other 1, 2, 3, 4 carbons that come along with it. All right, and again, there's really nothing conceptually all that different from what we learned before. The difference is that you get these big, ugly products because they got a bunch of carbons on them, right? They're much, much bigger functional groups that we're sticking on there. So for this one in particular, I got to include not only my carbonyl carbon, but I also got to include this whole cyclopentane ring on the back end there as well. Right? And again, counting carbons will be really important. You should have the same number of carbons on the left-hand side as you have on the right-hand side. You'll get really good at drawing your shapes by the end of this semester. All right? Cool. All right, so we'll finish up with this next class.